Hey everyone, if you've got your drinking water exam coming up, you are in exactly the right place. We're about to do a high yield, super focused review of Unit 3 water treatment, and we're going to hit every single key concept you need to absolutely master for your test. So take a look at this. This is the big picture, the entire roadmap our water follows. It comes in as raw influent, goes through all these different stages, and comes out the other side as clean, safe effluent. We're about to dive into each one of these steps. And that really brings us to the fundamental question, right? How in the world do we take water from a river or a lake, water that's full of all kinds of stuff, and turn it into something that's perfectly safe to come out of your tap? Well, the answer is a really clever multi-stage process, and we're going to break it all down. Here's our game plan. We'll kick things off with why we even bother treating water. Then we'll trace its path through four crucial stages: sedimentation, coagulation, filtration, and finally, disinfection. And we'll wrap it all up with a core concepts review to make sure it all sticks. Let's get into it. Okay, first things first. Before we jump into the how, we need to be crystal clear on the why. Why are we doing all this? And we also need to define a couple of key terms that I promise you are going to pop up on your exam. You can really think about these objectives in two main buckets. First, there's the aesthetics, making sure the water doesn't look weird, taste funny, or smell bad. Then there's the safety and utility part, getting rid of impurities, hardness, and things that cause corrosion. But the single most important goal, the number one reason we do all of this, is to remove pathogens. Those are the nasty, disease-causing microorganisms. The whole point is to make water safe. Okay, this is a big one for your exam, so pay close attention. You need to know the difference between unit operations and unit processes. Unit operations are all about physical or mechanical methods. Think screens or filters. Unit processes, on the other hand, involve chemistry or biology, like adding chemicals for coagulation or chlorine for disinfection. Just remember, operations are physical, processes are chemical. Got it? Good. All right, let's dive into the first major stage of treatment: sedimentation. This is where we step back and let a fundamental force of nature, good old gravity, do all the heavy lifting for us. The concept here is actually super simple. Think about a glass of muddy water. If you just let it sit, what happens? All the heavy stuff, the silt, the sand, the clay, it all slowly sinks to the bottom. That's exactly what we're doing here, just on a massive scale. We hold the water in a giant tank and let gravity do its thing. Now, to make this work efficiently, we have to get a few things just right. The flow of water has to be incredibly slow, almost still. The detention period, that's how long the water hangs out in the tank, is usually around 3 to 4 hours. And we also carefully control something called the overflow rate to measure how well it's working. All these factors together maximize just how many of those solids we can get to drop out. So, sedimentation is awesome for the big, heavy particles. But what about the really, really tiny stuff? I'm talking about the particles that are so small and light they just float around forever and will never settle on their own. Well, for that, we need to bring in some chemistry. Welcome to stage 2, coagulation and flocculation. This is basically a 3-act play. First, we have flash mixing, where we dump in some chemicals called coagulants and mix them up really fast. Second is flocculation, where we gently stir the water to encourage all those tiny particles to start clumping together into bigger chunks we call flock. And finally, it's back to sedimentation, but this time we're letting that heavy, newly formed flock settle out. The science behind this is so cool. See, all those tiny little impurities have a negative electrical charge. It's like trying to push the negative ends of two magnets together. They just repel each other. That's why they never clump up. So, the coagulants we add have a positive charge. They swoop in, neutralize that negative charge, and poof, the barrier is gone and the particles can finally stick together. Now, there are a bunch of different coagulants out there, but if you remember just one for your exam, and you absolutely should, it's this one, aluminum sulfate, better known as alum. It's the MVP. It's cheap, it's reliable, and it works incredibly well. It is the go-to choice for a reason. Okay, after coagulation and sedimentation, the water is looking way, way clearer. But it's not quite ready for prime time yet. To get rid of the last little bits of fine particles and even some microorganisms, we move on to the polishing step, filtration. Filtration is an absolute powerhouse. Seriously, just by passing water through beds of sand, we physically strain out whatever is left. This pretty simple process can remove up to 99% of bacteria, so it's not just making the water clearer, it's making it a whole lot safer, too. When it comes to sand filters, there are two main players you need to know for your exam: the slow sand filter and the rapid sand filter. And just by looking at them, you can probably already spot some differences in how they're built. So let's break down what makes them different because it's really important. Okay, exam alert. This table right here is classic test material. Slow sand filters need a huge amount of space and they work slowly, but they are amazing at removing bacteria. Rapid sand filters are much smaller, way faster, and they get cleaned every day by a process called backwashing. But here's the key difference in what they do. Rapid filters are great for getting rid of turbidity, that's cloudiness, but slow filters are the champs at getting rid of bacteria. Why? Because a thin, living, biological layer forms on top of slow filters, and it literally eats pathogens for lunch. So we've removed the big stuff, we've removed the small stuff, and we've polished the water. But now we come to what is arguably the single most important step for public health: disinfection. This is the final firewall, the critical barrier that makes sure any remaining bad guys are neutralized for good. So what makes a perfect disinfectant? Well, it's a tricky balancing act. It has to be absolutely lethal to pathogens, but totally harmless to us. It needs to work fast, it needs to be cheap and easy to get, and you've got to be able to easily measure how much of it is in the water. And the one method that has fit that bill for over a century, the one used all around the world, is chlorination. Adding chlorine to water is the absolute cornerstone of modern water disinfection. Now, you absolutely cannot talk about chlorination without understanding this graph. This is the breakpoint chlorination curve, and I promise you it is essential. It shows us what happens to the chlorine level in the water as we add more and more chlorine to the water. It's not as simple as you might think. Let's walk through this curve together. When we first start adding chlorine, it gets immediately eaten up by impurities. Then, as we add a little more, it starts reacting with ammonia in the water to form something called chloramines, and you see the line go up. But then something weird happens. As we add even more chlorine, it starts destroying those chloramines, and the chlorine level actually drops. The lowest point of that dip, that's it. That's the break point. Only when we add enough chlorine to get past that point do we get what we're looking for: a stable, free residual chlorine. And that free residual is the goal. That's the magic stuff that stays in the water, protecting it all the way through the pipes to your house. All right, we have officially followed a drop of water all the way from the river to the tap. So let's lock in all that knowledge with a final, rapid-fire review of the absolute must-knows for your exam. Okay, here's your final cram sheet. The goal? Make water safe from pathogens and pleasing to the senses. Unit ops are physical. Unit processes are chemical. Sedimentation lets gravity do the work. Coagulation uses chemicals, especially alum, to make tiny particles clump into flock. Filtration uses sand to polish the water. And you better know the difference between slow and rapid filters. And finally, disinfection uses chlorine to kill pathogens, and the key is to get past the breakpoint to achieve that protective free residual. If you can lock these points in, you've got this. Good luck on the exam.